Welcome. I, Abhinav Sir, welcome you all on India's largest live learning platform, that is Gradeup. Okay, my friends, yesterday we have planned a session, but due to some protest in Delhi and NCR region, we are not able to do the video or to take the we are not able to take the class yesterday. So I am taking the class of strength of material today, and our topic for today will be elastic constant and Hooke law. An important topic, and in various other topics also this topic is used. So indirectly or directly this topic will help you in many ways in GATE exam, not only in this SOM subject but in other topics, but in other subjects such as fluid also. So you must have a basic knowledge about these constants, and believe me, my dear students, if you take a complete video of my today on this elastic constant, you definitely will be having a great concept of these constants and you can solve any type of question. Okay, so in this session, which will be about 1 hour or so, please stay tuned and you will have a complete knowledge of this topic and you can solve the questions very easily. Okay, so my friends, let's go. This is my brief introduction. Please take a screenshot of it. Okay, just kidding. This will not be asked in your exam. Okay, let us go further. So I am taking all elastic constants one by one. First of all, I am taking, my friends, Young's modulus, or that is sometimes called as modulus of elasticity and represented by capital E. Okay, and it is represented by, my friends, by capital E. Okay. Now, what is E, that is Young's modulus? My friends, Young's modulus is stress by strain, stress divided by strain. Normal stress by normal strain, my friends. Normal stress by normal strain. Normal stress is that stress which is perpendicular, that is normal to that area. My friends, you must know this, and I hope that almost all of you know this, but my friends, there is a point behind this, that Young's modulus is stress by strain, but only and only for uniaxial loading. Young's modulus is the ratio of normal stress by normal strain, but only for uniaxial loading. Uniaxial loading means, suppose this is a bar like this and this is fixed here, and I apply a force here like P, then this force will cause some stress, and stress will be P by A, of course. Then this stress by strain, that is elongation in this bar in this normal direction, in this direction of this P, this stress by strain is Young's modulus. But this relation is valid only and only for uniaxial loading. If, my friends, this is a bar and I apply some force here and some force here, and suppose it is fixed, my friends, then for, suppose I apply a P force here and a Q force here, then for this I cannot write, suppose I am taking this direction first, I cannot write stress by strain is Young's modulus for this direction. Suppose in this direction stress is, suppose I'll take it as P1 by A. So stress is P1 by A, then stress by strain in this longitudinal direction I cannot write as Young's modulus. So I can write, my friends, stress by strain is Young's modulus only and only for uniaxial loading, like this. Okay. So stress by strain is Young's modulus, normal stress by normal strain is Young's modulus for uniaxial loading. Okay. My friends, let us take the next elastic constant, that is modulus of rigidity, or sometimes it is also called as shear modulus. My friends, Suppose this is a body, my friends. Suppose this is a body. I apply a shear like this. Suppose we have already derived in our previous session. These all stresses are equal. If this is tau, this is tau, this is tau, this is tau, all are equal. We have derived that. Now, after applying or after this body is having this kind of stress, my friends, the deformation will be something like this, and the angle earlier was 90. Now the angle is suppose 90 minus gamma. So this gamma is shear strain. My friends, this gamma is shear strain. Okay. Then, my friends, shear stress is directly proportional to shear strain. If I apply more shear stress, on this plane or in this body or on this point, then deformation will be more obviously. If I apply more shear stress, then deformation, that this angle change will be more, gamma will be more definitely. So, more shear stress, more shear strain, they will be directly proportional. And to remove that proportionality sign, we use G. Tau is equal to G by gamma. G is what, my friends? G is modulus of rigidity or shear modulus. So, G is equal to shear stress by shear strain. So, my friends, it's simple. Normal stress by normal strain is Young's modulus, one elastic constant. And second elastic constant is shear stress by shear strain is shear modulus, or sometimes called as modulus of rigidity. I am again repeated. Normal stress by normal strain, Young's modulus. Shear stress by shear strain, that is shear modulus or modulus of rigidity. Okay, most of you have joined. Hello Shishir, I hope you are fine. Hello Anusha. Okay, Anusha is saying, what about other subjects? Please be in touch with Gradeup app and our channel. Soon we are launching our different other subjects as well. Please be in touch with Gradeup app and subscribe our channel. Notification will be gone to you also. Okay. Now, hello ABC. Good. ABC is saying good to see you again. Thanks ABC. Good to see you also. Okay. Now Inzamam has joined us. Hello Inzamam. Hello Akshay. Hello Ashish. Okay, you can see this session on app, on Gradeup app and YouTube both. Okay, most of you, hello Surendra, most of you have joined in app and some of you also joined in Gradeup app. Okay, I'm again repeating, normal stress by normal strain is Young's modulus and shear stress by shear strain is shear modulus. Okay. Mohit Dubey, he might be my offline friend. He is saying my tagline. Okay. Next, going further. Next is bulk modulus. My friend, what is bulk modulus? Suppose, my friend, this is a body. I am showing body like this, and my friends, on this body, suppose some stress is acting like this, some stress is acting like this, and some stress is acting like this in 3 direction. Then K is hydrostatic stress upon volumetric strain. Volumetric strain means delta V by V, change in volume by volume. Normal strain is what? Change in length by delta L by L. Similarly, volumetric strain is delta V by V. My friends, see, once again, I have discussed normal stress here. So, normal stress by normal strain is Young's modulus, all of you know. But the 2 points here which we have to focus till now, that normal stress by normal strain is Young's modulus only and only for uniaxial loading. For multi-axial loading or for biaxial loading, multi-axial means stresses in all 3 directions. Biaxial means stresses in 2 directions. At what time, what will happen, that we will see in Poisson ratio chapter, that we were going to discuss, that I am going to discuss in next week. So, stress by strain is Young's modulus only for uniaxial loading. First point is this, that we have seen up to here. And second point, my friend, is this. You all know that bulk modulus is stress by volumetric strain, that is delta V by V. But you miss one point, is that my friend, that is sigma by volumetric strain delta V by V, but that is Bulk modulus is only and only derived or defined for equal and alike triaxial stresses. Means this all three should be sigma, sigma, sigma. It may be tensile also, but in that case also magnitude should be same. Sigma tensile, sigma tensile, sigma tensile. Okay, I am again saying bulk modulus is only defined for equal and alike triaxial stresses. All three stresses should be same. There must be three stresses and they must be of same magnitude. May be tensile also. They can be tensile also. But all three should be, if tensile, then sigma, sigma and sigma. So bulk modulus is only defined for equal or triaxial stresses, or sometimes in fluid mechanics when you are dealing with bulk modulus, sometimes they also called as hydrostatic stress. Why? Because hydro means water, static means ruka hua. Hydro means water, static means ruka hua, in rest position. When water is in rest position, my friends, then stress at or pressure at H depth below is gamma H in all directions, and it is equal, gamma H in every direction. My friend, suppose this is a bottle and I go up to this point, then stress will be or pressure will be gamma H, H height below the water level, and this stress will be equal in all direction. If I put a hole here, then water come here. If I put a hole here, then water comes towards you. If I put a hole here, then water goes here. And so stress is at equal direction. Wherever it will get opening, it will go out. Water will go out. So it is called a hydrostatic stress, because hydrostatic stress, hydro means water, static means at rest. So when water is at rest positions, pressure at any depth below, that is gamma H, is equal in all directions. So bulk modulus is only defined for equal and alike triaxial stresses. All three stresses can be compressive, can be tensile, but they should be of equal magnitude. Only for that case bulk modulus is defined. If this is 2 sigma or this is 3 sigma, then in that case there is no meaning of bulk modulus. So bulk modulus is hydrostatic stress or equal or alike triaxial stresses upon volumetric strain. Volumetric strain means delta V by V. Okay, my friends, can any of you tell me the bulk modulus of a rigid body? My friends, can any of you tell me bulk modulus of rigid body? Or I can say incompressible body or fluid, bulk modulus. Please, you can write in comment box. Those who are seeing in Gradeup app, they can write in that chat box. Those who are seeing in YouTube, they can write in YouTube comment section. Okay, most of you have joined here. Hello Sanju. Sanju is asking what is strain energy. Okay. Sanju, strain energy I can tell you here also, but I think when we are covering deflection chapter, that time it will be more. Till now, Sanju, you can see this. Suppose a bar is elongated. So I am doing a work, Sanju, in that bar for elongation. So that work is stored in energy. So when I have elongated a bar, I have applied some work, and that work is stored in that body. That energy is called strain energy. Okay. So most of you have answered right, 0.5. Budhev is saying, hello Budhev. Budhev is answering 0.5. Amandeep is saying 0.5. Keval Rawat is saying 0. Anusha is saying infinite. Okay. See, my friends, for rigid or incompressible body, my friends, for rigid body or incompressible, volume changes how much? 0. That is why it is called rigid. Volume can't be changed. Incompressible means it can't be compressed. It can't be compressed. Volume can't be compressed. Delta V is 0. So if delta V is 0, then K for that material will be infinite. Incompressible. Incompressible means delta V will be 0. Delta V change in volume will be 0. So delta V will be 0, denominator will be 0, then K will be infinite. Obvious, yaar. So for incompressible body, this will be infinite. Okay. Now going further, my friends. Okay. So we have derived first Young's modulus, normal stress by normal strain. Then we have defined shear modulus, shear stress by shear strain. Then I have told you bulk modulus, that is sigma hydrostatic stress by volumetric strain. Now I am going further for the last elastic constant, that is Poisson ratio. My friends, see here. See, suppose my friends, this is a body, I apply a P forces, I apply a P force, this, please see this Poisson ratio constant very carefully. If I apply P force like this, if I apply P force like this, my friends, then on this body I am applying a tensile force, then length will be increased and simultaneously width will be decreased. So Poisson ratio is negative of lateral strain, divided by longitudinal strain. My friends, please see here carefully. Poisson ratio is negative of lateral strain by longitudinal strain. I am telling you everything. Why it is negative? I am telling you everything. First see here. Now, what is lateral? What is longitudinal? This strain is longitudinal. This along the length. And this is lateral. My friends, what is the basic definition of lateral and longitudinal? My friends, the longer axis is longitudinal and smaller axis is lateral. Most of you have think like this, but that is totally wrong concept. That axis will be treated as longitudinal axis where the force is acting. Since in this bar force is acting like this, since in this bar force is acting like this, therefore this axis will be longitudinal axis and all axis perpendicular to that will be treated as lateral axis. If my friends see here, if on this same body I apply a P force like this, I apply a P force like this, then on the same body, this direction where force is acting will be as longitudinal axis and the perpendicular to it will be lateral axis. So longer axis is longitudinal and shorter is lateral. That is not good point. That is totally incorrect. My friends, that axis where load is acting or stress is acting, that axis is longitudinal axis. If load is acting like this is longitudinal. If load acting is like this is longitudinal. And all other will be lateral. If this is longitudinal, all 90-degree axis to it will be lateral. If load acting is like this, all 90-degree axis will be lateral. My friends, of course, with this kind of force, it will elongate here, but it will contract like this. The shape, my friends, will be like this. Now, my friends, why there is a minus sign here? Suppose, please, my friends, listen here carefully. Suppose I take tensile stress is positive and compressive strain as negative. I am again repeating. Suppose I take tensile strain means elongation as positive and compression, contraction, deformation as negative. My friends, this longitudinal, that is along the force is positive. This is positive. And lateral, it is contracting here. So length is reducing. So from this sign convention, this will be minus. So minus upon plus will be minus. So there is a minus sign more. So mu will be positive. Let us go here, my friends. Let us go, my friends, here. In this direction, length is increasing. So this is longitudinal direction. Then my friends, this is positive again. And in lateral direction, it is reducing. Therefore, it is minus. Minus upon plus will be minus. And there is a definition minus also. There is a minus in definition also. Then it will be, my friends, again positive. So mu will be positive. My friends, let us go further. Okay. Someone has asked a doubt that what happened if load is acting inclined. Sejal, if load is acting inclined, then we have to resolve those load into two axes. Okay, but for inclined load, Poisson ratio will not be asked in your syllabus. But if it is, then we have to resolve it in two direction. Okay, see, Poisson ratio for cork is 0 and for other things it will be in this range. Of course, you don't have to remember this data, and for perfectly plastic material, that is on for rubber also, it is 0.5, and so for human tissues and polymers, mu is in negative. My friends, please listen what I am telling very carefully. Mu will be, these mu's you will be finding very easy, because I have shown you here that if one is increasing, other is decreasing. So by after putting one more minus sign, again it will come as positive. If it is increasing here, it will be reducing in other side. So one will be plus, one will be minus, and after a minus sign again in formula, that will be plus. So these you are getting correct. But what about cork, my friend? What about cork? See, cork mu is 0. That is, if this is cork na, my friends, if this is cork na, and you apply load like this, then mu is 0. My friends, mu is 0 means that lateral strain is 0. Lateral strain is 0 means, my friends, after this, the elongation will be only in this direction, in longitudinal direction. Therefore, for this mu will be 0, because lateral strain is 0, cork. Now, why that is 0, I will tell you. Now, for human tissue, mu is negative. My friends, I am writing here again formula, mu is equal to minus of lateral strain upon longitudinal strain. So mu is negative for soap, polymers and human tissues. So mu is negative means these lateral strain and longitudinal strain. This lateral strain and this longitudinal strain both are in same sign. Either they will be plus plus or they will be minus minus. Then it will come in negative. Plus plus or they will be in minus minus. Means they are both increasing, plus plus, or they both are decreasing, minus minus. Therefore, if I draw for this human tissues and polymer, suppose this is human tissue or soap polymer, suppose this is polymer, and if I apply a P force like this, then my dear friends, the deflected shape will be somewhat like this for soap polymer. And see, if deflected shape is like this, then longitudinal strain, my friends, along the force is positive, increasing, and lateral is also positive. So both are of same sign. Longitudinal here also positive along the force, and lateral, that is 90 degree to force, is also positive. Both are increasing. So this plus plus will be, and there is a minus in the formula itself. Therefore mu will be coming in negative. Similarly, my friends, let us draw one more figure. If this is a soap polymer and this is a soap polymer, and I'll apply a force like this, then this deflected shape will be like this. Longitudinal along the force is negative, lateral is also negative. In longitudinal axis along the force, it is decreasing, and in lateral, it is decreasing. Therefore, both are decreasing, therefore both are negative. Negative sign cancel out, and there is a minus in the formula itself. Therefore, mu will be negative. Now, my friends, from common sense, my friends, see here. Yes, most of you are commenting. Inzamam is saying your teaching wins our heart. Okay, yes. If that is there, okay, that's very good. That's a very motivational and boost up for any faculty if you are saying like this. My friends, if mu is negative, then I have shown you applying this force, it will be elongating in longitudinal direction, it will be elongating in lateral direction. Similarly, it will be contracted in this direction and in this direction. Both are of same sign. Therefore, they will cancel out, and there is a minus in the formula, so mu will be negative. My friends, by common sense, you see that, yaar, why this can happen, yaar? Why this can happen that it is increasing in this direction also, in this direction also? How this can happen, sir? This is decreasing in this direction also, and this is decreasing in this direction also. How can this happen, sir? I am not able to visualize it, sir. How this can happen? So, my friends, before telling you this concept, let me tell you one thing. You say this t-shirt is of blue color. Because from your childhood days, your teacher and your parents say it is blue. You say this logo is of green color. Because from your childhood days, your parents, your teacher say it green. You say that Gradeup is written is in white color, sir. Because from your childhood, your teachers, your parents say it is white color. But what happen if suppose today, that is 20th December, a newborn baby is born, and from his childhood only I say that this logo of Gradeup, this color is red color. This color is red. His friends, his teachers, his friends, neighbors, and his girlfriend after some years, everybody tells, everybody teaches his, this is red color, this is red, this is red. Then after 10 years, 20 years, if you give him this color, what is this color, this logo color, he will say red. Similarly, from your childhood, you are saying that volume is constant, volume is constant. But volume is, suppose in your 8th class, in your area volume measurement chapter, there are some questions like there is a sphere, diameter is like this. Suppose you mold that sphere and you, after molding, you make it small cylindrical bullets, then how many bullets will be formed? I'm again saying the question, there is a sphere, there is a big large sphere, diameter is given, and from that sphere you are molding that sphere and you are making small cylindrical bullets. That how many bullets can be made? So you are equating the volume. So from your childhood, my friends, you are saying that you are seeing that volume is constant, but that is only valid for rigid body physics. On the first session itself, I told you that so is deformable physics. The distance between 2 points can change. So volume can change, my friends. Okay, not understood yet? Let me draw the figure then. See, suppose, see my friends, suppose this is, please very carefully see this. Suppose this is a figure, okay? What is this figure? Let me tell you. Suppose to a soap polymer or anything which has a mu negative or anything which has a mu negative, my friends, if you take a microscope and from that microscope you see a molecule, those molecules will be like this, and these all are hinges, okay? For anything which has mu negative, for a very microscopic level, if you see that, this will be like this. Suppose I apply a force P like this, and these are all hinges, my friends. These are all hinges, like this my elbow. Okay, these are all hinges. By applying this force, my dear friends, then by applying this kind of force, since these are hinges, please visualize this, then this bar goes like this, or not bar, this molecule goes like this. These are hinges. After putting a force like this, you can easily see that this will go in this shape. So volume increases, my friend. Since these human tissues and soap polymer, if you see them from microscope, then those molecular arrangement will be like this. By pulling it like this, the volume is increasing, my friends. Okay, my friends. So many of you are asking, so what is the value or range of Poisson ratio? Let me tell you a very interesting thing about this, my friends. For metals, if mu is asked, then it ranges from, for elastic material, mu ranges from this range, 0 for cork and this for rubber. But for engineering materials, mu ranges from 0 to 0.5. But if you take all materials, my friends, including human tissues and soap polymer, then mu ranges from, my friend, minus mu to 0.5. See, let me tell you a very interesting fact. GATE has asked a question and most of you are learning this 0 to 0.5, but answer given was like this. Then after 5 years, again GATE has asked, and every people who is seeing the previous year and who is discussing about from his seniors, he knows that mu is like this, minus 1 to 0.5, minus 1 to 0.5, minus 1 to 0.5, and GATE has given this answer. I am again saying, first GATE has asked a question, most of you have written this, but answer was this. Then again after 5 years, GATE has asked a question, because in previous year paper you have seen the solution, you have written this, but answer now they give like this. So what answer you have to write in exam? My friend, if in question that find the range of mu for elastic material or engineering substances or engineering material, then answer will be this one, this red, 0 to 2.5. I'm again saying, if in exam question is asked that find the value of mu for metals or engineering metals or engineering substances, then answer is this. But if in exam the question is asked find the value of mu for all substances in this earth, then of course the answer will be this. I'm again saying, if in question it is asked that find mu for all substances in earth, it is this, and if it is asked for elastic material and metals, this is this. So the gate has not given different answer. Actually the question was different. When the question was for all materials, for all substances in the earth, then -1 to 2.5. But if in question again after 5 years they have only asked for metals or engineering materials, then answer will be this. Okay. Now again my friends, yes, Shubhankar is saying, sir please explain lateral strain. My Shubhans, what is your Shubhankar? If this is a body, I apply a P force like this, then my friend, it will elongate in this direction due to this force, and simultaneously it will decrease in this direction. That is lateral strain. Lateral strain means perpendicular to this load. It is decreasing, that is lateral strain. Okay, so till now we have discussed about E, normal stress by normal strain, but only for uniaxial loading. I have discussed G, shear stress by shear strain. I have discussed K. K is hydrostatic equal and allied stresses. All three stresses should be equal upon volumetric strain, delta V by V. And Poisson ratio is negative of lateral strain upon longitudinal strain. These are 4 elastic constants. Okay. And the relation between these elastic constants will be like this. You have to remember this formula. I can derive also, but I don't want to go in derivation and waste much of time. Instead of that, I can take a question more. Okay. Inzamam is asking, sir, are you completing this whole subject? See, Inzamam, till now we have planned for the first chapter. I will deal it thoroughly. For any competition exam, I will teach the first chapter thoroughly. What will be in first chapter? Elastic constants, stress strain curve, properties of material, stress, strain, thermal stresses, and Poisson ratio in detail we will deal in next week. Deformation of bar. But for other chapters, please keep in touch, subscribe our channel, or please follow me on Gradeup app, that is Abhinav Negi. You will get a notification for other as well. We will definitely teach you those other topics also, and tell the timing also. Okay. Now going further, these are the relation between elastic constants. Inverse of mu is modular ratio. My friends, what is the number of independent elastic constants? My friends, till now we have dealt with 4 elastic constants, and till now whatever the elastic constants I have told you, that is E, normal stress by normal strain, G, shear stress by shear strain, bulk modulus, sigma, hydrostatic stress upon volumetric strain, and mu. Those all are told by me for isotropic material. Our assumption for all those definitions that I have told you, that material is isotropic or homogeneous. For those we have 4 elastic constants. My friend, again there is an interesting question in GATE, that sir, that the question was, what are the number of elastic constants for isotropic material? I am again saying, these 4 elastic constants that I have told you, those formulas or those explanation are only assumption was for isotropic material or homogeneous. Those all 4 definitions are only for isotropic material. My friends, so number of elastic constant, one important question, a trick question. Number of elastic constant is of course 4. E, G, mu, K. These 4 are elastic constant. But my friend, if total number of elastic constants are asked for isotropic, it will be 4. But my friend, if it is asked for number of independent elastic constant, then my dear students, I must tell you it is not 4, it is 2. My friends, it is not 4, it is 2. Independent, my friends, see these relations. If you know, suppose I am again telling, suppose you know G and mu only 2. Suppose you know G and mu. Then from this relation, if G is known, if mu is known, then E will be known. So only from G and mu, I can find out E. G known, mu known, E can be found out. And if E can be found out, mu is already known, E can be found out like this. From this relation, mu is already known, then K will be known. Then only by G and mu only we can find 4 elastic constants. They are already known, we have derived E and K. I must again tell you. Suppose G and mu is known, G known, mu known, G known, mu known, G known, mu known. Then from this relation, E will be known. Now E will be known, mu is already known, then K will be known. So from only 2 elastic constants, I can derive all 4. Okay. So number of independent elastic constants 2. If in question it is asked, find the total number of elastic constant for isotropic, it will be 4. But if it asks for independent, then it will be 2. For orthotropic, my friends, it will be 9 and 21. Okay. Yes, Tejinder, you were absolutely right. Yes, Maheshwar, you were right also. My friends, in our syllabus of GATE and ESE, the only syllabus is for isotropic. In syllabus, we don't have to deal with orthotropic or anisotropic. But let me tell you a brief explanation about them also for further use. My friend, see, what is orthotropic material, what is anisotropic material, what is isotropic, what is orthotropic, what is anisotropic, what is homogeneous. I am dealing with all 4. See, what is isotropic material, my friend? Suppose this is a body and this is a point and this is B point, my friend. If in A point property in any direction, this, any direction, if property is same in any direction, and then this is called isotropic. Similarly, in B, property in any direction is same, then it is called isotropic. I am again saying, if at A point property in all directions are same, and if at B point property in all directions are same, then it is called isotropic material. Property at A and property at B might be different. But property, suppose Young's modulus at A in this direction, in this direction, in this direction, in this direction is same. And B Young's modulus in this direction, in this direction, in this direction is same. Then it is isotropic. Property A's property in X direction and B's property in X direction might be different. But A's property in X direction, in Y direction and in any theta direction, B's property in X direction, Y direction, in any theta direction is same. Then it is isotropic. My friend, what is homogeneous? My friend, if this is a body and suppose this is point A and this is point B, then A's property in X direction and B's property in X direction is same, then it is homogeneous. Similarly, if my friend A's property in Y direction and B's property in Y direction is same, then it is homogeneous. A's property in X direction and A's property in Y direction might be different if I am considering homogeneous. But if A's property in X direction, B's property in X direction and A's property in Y direction and B's property in Y direction is same, then it is homogeneous. Let me again tell you, please. If I am again, first of all, I am telling isotropic again, my friend. If A's property in X direction, A's property in Y direction and A's property in theta direction is same, A's property in X direction, A's Y direction, A's theta direction is same, then it is isotropic. B's property in X direction, B's property in Y direction, B's property in theta direction is same, then it is isotropic. for isotropic, it may happen that A's property in X and B's property in X might be different. Leave isotropic now. Come in homogeneous. If A's property in X direction and B's property in X direction is same, then it is homogeneous. If A's property in Y direction and B's property in Y direction is same, then it is homogeneous. Same for theta angle also. It may happen that A's property in X and A's property in Y might be different. It is homogeneous. But for isotropic, A's property in X, A's Y, all should be same. Our basic assumption in SOM that our material is isotropic also and homogeneous also. All points, all property, all directions same. Everywhere you will see in SOM, material isotropic and homogeneous. Every point, every direction, everything is same. Because everywhere you will see that in every chapter assumption will be homogeneous and isotropic both. Okay. Now, isotropic will be 2, orthotropic 9, anisotropic 21. What is orthotropic? My friend, if this is a body and I apply a force here, suppose you will be confused by this body. Let me take another body. Suppose let me take a cube. If I apply sigma stress here, then there will be strain. Suppose strain will be, suppose 2 will be strain. Suppose I take again the same size body, same material and apply a force sigma here. And suppose if I again take same size body and same material and I apply a sigma here. Then if material would be isotropic, in isotropic material, properties in any direction are same, then therefore this strain will be 2, this strain will be 2 and this strain will be 2. Because property is same. Suppose this is a small point and I am enlarging this and showing it as a cube. Suppose this is a small point. These three are, suppose in this beam, this is a point and I am enlarging this to this, to this and to this. If this material would be isotropic, in isotropic property in every direction is same, therefore if in this direction strain is 2, therefore same stress, same material, same dimension, this is 2 and here strain will be 2. But orthotropic material property is different in X, in Y, in Z direction. Therefore this might be 2 strain, this stress might be causing 2 strain, this might be some different 3 strain and this stress might be causing some different strain 1. So if due to same stress in same body, strain in 3 directions are different, then this will be orthotropic. And what will be anisotropic? My friends, if we apply stresses here, in orthotropic material only strain will be occurring in X direction, in Y direction, in Z direction, although all 3 strains are different. But in anisotropic material, if I take like this, then my friend, due to these 3 stresses, shear strain will be different. Shear strain will also come. I am again saying, if these 3 materials are isotropic, then due to this at this stress, strain in X direction suppose is 2, strain in Y direction suppose as 2, strain in Z direction is suppose as 2. All 3 strains will be same because for isotropic, property in 3 directions are same. Orthotropic, property in 3 directions will be different. Strain by this stress will be 2, suppose this stress might be 3 and due to this stress might be 4 because property in all directions are different. But there will be no shear strain due to in orthotropic material. But in anisotropic material, due to these 3 stresses, not only longitudinal strain, shear strain might come. Okay. My friend, I am again telling you just in brief, for isotropic, all 3 will be having same strain. For isotropic, all 3 will be same strain. For isotropic, all 3 will be having same strain. For orthotropic, these 3 will have only normal strain, but they can be of different magnitude. And in anisotropic, these 3 will be having normal strain of different magnitude and they will be having shear strain also. In these 2 cases, no shear strain. Okay. Let me take a question, my friend. Please solve this question. Maheshwar said, what is contraction ratio? Of course, that we will discuss in our next class. There are deformation of bar. Okay. Please, my friends, solve this question. Modulus of elasticity is given and modulus of rigidity is given. What is given, my friends? E is equal to 200 gigapascal and modulus of rigidity, that is G, is given as 80 gigapascal. What are they asking? They are asking for mu and K. So it is easy, yaar. I already told you that if you know two elastic constant, then you can find any other two also. From only two you can find all. E.g., you have to find mu and K. Okay, suppose let me take you here and we have these relations here, and what was the question? E 200 and G 80. Okay, let us come here. E 200 and G 80. E 200, let us take this formula. E is 200 and G is 80. So right in applying on this formula, 200 is equal to 2 into 80, that is 160, 1 plus mu. So 200 by 160 is how much? 200 by 160, 5 by 4, then it is 1.25 is equal to 1 plus mu. Then mu will be 0.25. Okay, mu we are getting. Now what are they asking? They are asking K also. Oh my God, they are asking so much. Let us find out K. So putting in this relation, E is how much? On first relation, first relation, my friend, see there. 200 is equal to 3K. 1 minus 2 mu. Mu we got 0.25. So 1 minus 0.5. So 1 minus 0.5 is how much? 0.5. 200 by the this will be 200 upon 0.5 is equal to 3K. So K is equal to 400 by 3. So it will be 133.3. Mu 0.25, K 133.3. So my friends, this is K and mu. Okay. Inzamam is saying correct answer D. Mohit is D. Mohit says mu 0.25. Okay, Ritesh 133.33. Oh, okay, 100% success ratio. Shivankar is saying D. My friend, lovely. Lovely to see all students who have given the answer, all are correct, and many of you have given the results, your answers in YouTube and an app also. Very good. I hope in further question also you are doing like this. So this is a body, dia 25 mm, length is 1 meter, this length is 1 meter, dia is this, epsilon D, epsilon L, longitudinal strain, and epsilon D is diametrical strain. They are asking find all elastic constants. Let us first of all find out mu. Mu is equal to minus of lateral strain upon longitudinal strain. Let me solve also, and who knows the solution, they can solve your own also. So mu is minus of lateral. Suppose what was lateral, what was longitudinal? I am again telling, in the direction where force is acting, it is longitudinal, and in 90 degree it is lateral. So in longitudinal direction and lateral direction is perpendicular to the force. Force is this is longitudinal, this is lateral. So lateral is how much? Minus 1 into 10 to the power minus 6 along the diameter. And longitudinal is how much? 3 into 10 to the power minus 6. So mu is equal to, of course, 1 minus will be also there. This minus, this is epsilon D, this is epsilon L, and 1 in minus in formula. This will be 1 by 3, that is 0.33. Mu is 0.33. All elastic constants they are asking. Okay, Aman is saying correct, mu 0.33, Mohit is 0.33, very good. Now, but let us found, we have found mu. Now, I am going to find out Young's modulus. My friend, what will be Young's modulus? Mu is 0.33, let me write here. Mu we got as 0.33. Now, let me go to finding out Young's modulus. My dear lovely friends, what will be Young's modulus? Stress by strain is Young's modulus for uniaxial loading, and in this question also there is uniaxial loading, so this formula will be valid. Okay. Aman Bhargav is saying, sir, stress tensor and strain tensor क्या होता है? Please, Aman, See my earlier lectures, that tensor I have stress tensor and strain tensor I have written and explained there thoroughly. I have written matrix also. Still, if you are after that video also, if you are having doubt, then you can ask me doubt in Gradeup app. Okay, Aman, see, do this question. So Young's modulus is stress by strain. Stress is how much? 600. Force by area. Area is pi by 4 into d square. Diameter is how much? 25 mm. So 25 square into 10 ki power minus 6. Because if we convert millimeter into meter, I'm doing everything in SI units. This is stress. What is strain? Longitudinal strain is how much? 3 into 10 ki power minus 6. Stress by strain is Young's modulus. From there you can find out E, and you will find out E, my friend, as from here you will get 407.6. Don't waste time in calculation. You can solve this expression and you will find out E as this. So E we got as 407.6 into 10 ki power 9 gigapascal. Okay. Now please find out G and K also. See here, the relation E is equal to 2G1 plus mu. E is equal to, my friends, relation is E is equal to 2G1 plus mu. My friends, mu is already known, E is already known. Simply by putting this, you can find out G. So from here, you will find out G as, let me not waste time in this, let me tell you, you will find G as, I think, 153.2 gigapascal. Please, you can check it later on. I am not wasting time in calculation. Concepts are more important. E is find out G, E, G, mu, K is remaining. So what will be K? Let me again see that formula. So E is equal to 3K 1 minus 2 mu. E is equal to 3K 1 minus 2 mu. My friends, mu already known, E already known. From here K will be, we are getting. And from here, my friends, K you can check on later on. I am not wasting time in calculation. It is 399.6 gigapascal. See, I am telling you the concept, telling you the expression. Should not waste time on calculation, that you can do. Okay, correct, Aman. Ashi is correct. Mohit is correct. Let us go further. Next question. A sphere is subjected to all around hydrostatic normal stress. Hydrostatic it is written. So in all directions stress is same. So we can apply that bulk modulus relation. That's why it is written hydrostatic. Find change in volume. Find change in volume. Okay, please do this question. So K is equal to sigma by delta V by V. So bulk modulus is given, yes, 10 ki power 5 Newton per mm square, that is 10 ki power 5 megapascal. Sigma is given, how much? 200. Delta V they are asking, how much is volume? Volume is 720. Of course, everybody know how to solve this. Delta V got as 1.44. Okay, good, good. Next question. If EGK, okay, this is a good question. If EGK denotes Young's modulus, G is shear modulus, that is modulus of rigidity, K is bulk modulus, then for elastic material means mu can vary from 0 to 0.5. Material, not for all substance. Elastic it is written. Elastic material means 0 to 0.5. Which of the following statement can be true? They are asking. Please solve this. Aman Bhargav is saying A. Aman, please check it once again. See, these are the relations. See that if you can solve something from here. Okay, please solve this. So we know one formula, that is between elastic constant relation, that mu is equal to, I think what we have seen here, mu is equal to 3k minus 2g upon 6k plus 2g. Mu is equal to 3k minus 2g upon 6k plus 2g. Okay, this was the relation here. Okay, now my friends, let us first of all take this relation g is equal to E, or let us take as g is equal to 2k. So mu is equal to 3k. If I put g as 2k, then 2k into 2, this is 4k, and 6k plus 2g, g as 2k, there will be 4k. This is positive, this is negative, so mu will be coming in negative. So not possible for elastic material. For elastic material, mu ranges from 0 to 2.5. So mu is negative, is not possible. So g can't be 2k. G can't be 2k. Next, let us say if g can be E. Let us see if g can be E. Suppose take this relation. So if g and E are equal, then both will be cancelled out. Then it will be 1, 2, 1 plus mu. So 1 plus mu is equal to 0.5. So mu will be how much? Mu will be minus 0.5. Not possible for elastic material. So if I take E and G equal, relation will be like this. So my friend, then E can't be equal to G. Therefore, if this E can't be G, then this is also not correct. K is equal to E. Of course, this is the only option left. It will be correct. Let us check. If K is equal to E, come here again. If let us K is equal to E, in this relation, let us see. K is equal to E, K is equal to E, both will cancel. Here it will be 1 by 3 and 1 minus 2 mu. So 2 mu is equal to 1 minus 0.33. 1 minus 0.33 will be how much? 0.66. So mu will be 0.33, which is possible for elastic material. So my dear friends, only option is this, it is correct. Okay. Okay, your A was for previous question, then it's absolutely correct. Okay, Aman, it was your for previous question. Okay, I understood it. Ashish Verma is saying C. Okay, Akhil is saying C. Ritesh is saying C. Correct. Now let us go to the last question. You remember the strain matrix? Strain matrix was something like this: epsilon xx, gamma xy by 2, or gamma xy by 2 like this. They were written like this, if you remember, gamma xy by 2, and here it was gamma xz by 2, and my friend, yes, like this, here it was gamma yx by 2. If you have not seen this, please, my humble request, see my earlier lecture also. Gamma yz by 2, gamma yx by 2, gamma, sorry, let me correct this, gamma zx by 2, gamma zy by 2, and this is epsilon yy. This was like this. So we have to find out shear stress in xy plane, that is tau xy is we have to find out. See, gamma xy by 2 is 0.001. Gamma xy by 2 is 0.001. Therefore, how much will be gamma xy? Gamma xy will be 0.002. Gamma xy by 2, see this, is 0.001. So gamma xy is 0.02. Shear stress by shear strain is equal to shear modulus. So shear stress is how much? Shear stress is how much? Shear strain into G. It is how much? 0.002 into G. G is given 200 gigapascal. So answer will be like this. No, sorry, 200 into 0.2, that will be 400 megapascal. Okay. Aman is correct, 400 megapascal. Okay. Langesh is saying hi, Lagnesh. I am fine. Hope you are also fine. My friends, see, this is green card. By taking access to the green card, you can give 140 plus mock test not only for GATE but for any other competitive exam also. Even by a green card, you can not only do or give mock test for GATE but for all other exams also. Even from a single green card, you can access to any exams mock test related to civil, and you can give it any number of times. My friends, this was our class on elastic constant. I hope now you have a better realization of these constants. And my friends, if you like this video, then please like it on YouTube or on app, or comment it, or you can also follow me on Gradeup app. Okay? Now, our next session will be on deformation of bar on 23rd September, that is Monday at 8:30 p.m. Please, from that class, be regular, because we are taking more numericals from that class, and I will tell you a method from which you can find deformation of any bar very quickly and in a very easier way. Okay, so on 5th Jan, we are also launching the solution of IES paper, engineering service exam paper, at 7 p.m. onwards. We will be live. Okay, prep smart, score better, go Gradeup. Thank you.